Hi, Stu Schwartz from MasterMathMentor.com. This is video non-essential AB14a. The topic is differentials, and it covers the AB manual pages 252 through 254. In our last section on linear approximations, we have seen how the tangent line can be used to approximate a function. We continue that line of inquiry, focusing on notation. We have defined dy dx to be the limit as delta x approaches 0 of delta y over delta x. Dy dx is an entity called the derivative. But now we can separate these and learn the actual meanings of delta x, delta y, dx, and dy. Shown is a graph of y is equal to f of x in green. We choose a point P, x, f of x on the curve. We now move a small distance of delta x to the right, recalling that the Greek letter delta means change, and we plot that point Q. The coordinates for Q are x plus delta x, f of x plus delta x. The change in height between P and Q is the difference in the y values of these points, which is f of x plus delta x minus f of x. We will call this difference delta y. So delta y is equal to f of x plus delta x minus f of x. In real life, we are interested in this change delta y. We want to know how much we grew in a year, so we subtract our height last year from our current height. We might want to know our change in net worth over the last quarter, so we subtract our monetary worth in January from our monetary worth in April. A baseball team might want to know how much it improved in a year, so it subtracts the number of wins last year from the number of wins this year. Now we draw the tangent line through P and extend this tangent line to the dotted vertical line and complete the small blue triangle. We call the base of this triangle dx. Note that the bases of the large red and small blue triangles are the same, so delta x is the same as dx. But the heights of the large and small triangles are not the same, far from it, and we will call the height of the small triangle dy. Now as Q approaches P, delta x and dx get small. The difference between delta y and dy also begins to get small, and we can see this on our graph. Our delta y is the red dotted line, and the corresponding dy is the blue. Notice that as Q gets closer to P, there is not much of a difference between delta y and dy. So we can say that when delta x, which is dx, gets small, dy becomes a good approximation for delta y. Why is this significant? We will find that sometimes it can be very difficult to calculate the important delta y, which we said is what we're interested in. But dy is an approximation for delta y, and that is easy to calculate. We know that dy dx equals f prime of x, so cross-multiplying we get dy is equal to f prime of x dx. This is called the differential form, and dy is called a differential. So again, reiterating, delta y is the true change in y, dy is the approximate change in y, and when dx is small, dy is a very good approximation for delta y. In number 1, we are given that y, which is f of x, equals 3x squared minus 8x plus 2. We would like to find both delta y and dy as x changes from 1 to 1.01. We are told that x is equal to 1. And since we want to find a change as x changes from 1 to 1.01, delta x, which is dx, is equal to 0.01. So the true change is delta y, which is f of x plus delta x minus f of x, which gives us f of 1.01 minus f of 1. Plugging in, we get 3 times 1.01 squared minus 8 times 1.01 plus 2 minus the quantity 3 minus 8 plus 2. Now, this calculation is not that difficult to do, even without a calculator, but it does involve some arithmetic. Our delta y is 3.0603 minus 8.08 plus 2 plus 3, and that gives us negative 0.0197. So as x changes from 1 to 1.01, y decreases by 0.0197. We graph our function y equals 3x squared minus 8x2 in extreme detail as x goes from 1 to 1.01. Delta y is the line, the vertical line in red, and we can see that it is 0.0197 lower than the value at x is equal to 1. We now find the approximate change in y. We use the fact that f prime of x equals 6x minus 8 and state the differential form dy is equal to f prime of x dx. So therefore dy at x is equal to 1 is f prime of 1 times 0.01, which is negative 2 times 0.01, which is negative 0.02. Notice how good an approximation dy is of delta y. The values are very, very close, and it was far easier to calculate. We see our results on the graph. Dy is the line in blue, which is just a little bit longer than delta y. In number 2, we have y equals x cubed minus x squared plus 3x minus 2. We would like to try to find the true change and the approximate change as x changes from 2 to 2.01. We have x is equal to 2, delta x equals dx, which is equal to 0.01. Our true change is delta y, which is f of x plus delta x minus f of x, or f of 2.01 minus f of 2. That is 2.01 cubed minus 2.01 squared plus 3 times 2.01 minus 2 minus the quantity of 8 minus 4 plus 6 minus 2. We now need to use a calculator for these, and we get 8.110501 minus 8, which is 0.110501. To find our approximate change, we find dy. We know that f prime of x equals 3x squared minus 2x plus 3, and therefore dy is equal to f prime of x dx, or f prime of 2 times 0.01. F prime of 2 is 11 times 0.01, and dy is equal to 0.11, which is a very good approximation for delta y. In number 3, we have y equals 3x minus 2 over x squared plus 4, and we would like to find the true change and approximate change as x changes from 4 to 3.95. We have x is equal to 4, delta x equals dx, which is negative 0.05. Our true change is delta y, which is f of x plus delta x minus f of x, or f of 3.95 minus f of 4. This gives 3 times 3.95 minus 1 all over 3.95 squared plus 4 minus 3 times 4 minus 2 all over 4 squared plus 4. Using our calculator, we get 0.502470 minus 0.5, and our delta y, our true change, is 0.002470. To find our approximate change, we find dy. We start with f prime of x. Using the quotient rule is 3 quantity x squared plus 4 minus 2x times 3x minus 2 all over x squared plus 4 quantity squared. And this gives negative 3x squared plus 4x plus 12 over x squared plus 4 quantity squared. We know that dy is equal to f prime of x dx, and therefore the differential dy is f prime of 4 times negative 0.05. F prime of 4 is negative 0.05 times negative 0.05, which is 0.0025. Again, a very good approximation for delta y. Regrettably, differentials are no longer in the AP exam. Remember that calculus goes back to the end of the 17th century, where there was no technology available for exact calculations, especially with small numbers. These took time, and the possibility of error was large. Approximation techniques were extremely time-saving and gave a good estimate of the true answer. But today we can easily get extreme accuracy using calculators, and approximation techniques are not necessary. Still, they are helpful and have some geometric implications, as we will soon see. In number 4, we wish to determine the volume of a bowling ball. The radius is estimated to be 4.3 inches with the largest possible error of 0.2 inches. We want to approximate the maximum possible error in calculating volume and the approximate percentage error. The most efficient way to do this is to take a string, wrap it around the circumference of the ball, then take the string and straighten it out and measure it. Then divide by 2 pi, and you will have an estimation for your radius. That was not done here. We just estimated the radius to be 4.3 inches. Probably there will be an error, and in this case we say that the largest possible error is 0.2 inches. So we have r to be 4.3, delta x, which is dx, is equal to 0.2, and since we know that the volume of a sphere is 4/3 pi r cubed, dv dr equals 4 pi r squared, so the differential form is dv equals 4 pi r squared dr. And therefore dv is equal to 4 pi times 4.3 squared times 0.2 to get 46.4704 cubic inches. So just a small error in estimating the radius will give us a very large error in estimating the volume. And that is because the radius is very important to our formula. Our approximate percentage error is dV over V. We know dV to be 46.4704, and our volume V is our volume when we use our believed value of R, and that would give 4/3 pi times 4.3 cubed. Doing the math, we get 13.95%. So a radius error of only 0.2 inches, which is about 4.7%, will give an approximate error in the volume of 13.95%. And that is because the radius is so important in calculating the volume. Make even a little mistake in approximating the radius and the volume error will be very, very large. In number 5, we have a teacher having a large rectangular whiteboard in his classroom. He invites one of his students to measure the length and height with a ruler, and from there to determine its area. With only a ruler, the student determines that the length is 20 feet, but he admits he could have made a possible error of up to 1.5 inches. The width is slightly easier to do, and he estimates the width to be 4 feet, but may have made an error of 0.5 inches. We would like to use differentials to approximate the error in calculating the area in terms of square feet of the whiteboard. As with problems of this type, when we have mixed units, we have to decide which unit we want to work in. First, we'll decide to work in inches. So L, length, is equal to 240 inches, and DL is 1.5 inch. W is equal to 48 inches, and DW is 0.5 inch. We use our formula for area, A is equal to LW, and now we take our derivative. We can take our derivative with respect to any variable we want to. I will choose a mythical t. Therefore, dA dt equals L times dW dt plus W times dL dt. That variable t doesn't matter because we're going to multiply both sides by dt to get the differential form. dA is equal to L dW plus W dL. We then plug in our numbers, 240 times 0.5 plus 48 times 1.5, and our dA is equal to 192 square inches. Since we want our answer in terms of square feet, we will then multiply by 1 foot over 12 inches times 1 foot over 12 inches to get 1.333 or 1.3 bar square feet. We could choose to work in feet. When we do that, we will have to deal with fractions. So L is 20 feet and DL is 1/8 of a foot. W is 4 feet and DW is 1/24 of a foot. So A is LW, and again, dA dt equals L dW dt plus W dL dt, and our differential form dA is equal to L dW plus W dL. We get 20 times 1/24 plus 4 times 1/8, and now our answer is 4/3 or 1.333 square feet. Students are always amazed at the effect of what they believe to be negligible errors in estimating the length and width. To scale, we can see the whiteboard in light blue, and in the right lower corner, we can see the effect of their error. That is how far off the calculation of area could be. If we look at dA over A, because we now know the actual area of the whiteboard is 20 by 4, we get 4.3 over 80, and that is a 1.67% error. The use of differentials can make sense of derivative rules we learned algebraically at the beginning of the course. Rather than approach taking a derivative using limits, we look at it from a geometric point of view. Let's show geometrically that the product rule holds, that the derivative of f of x times g of x is f of x times g prime of x plus g of x times f prime of x. Think of f of x as one dimension of a rectangle and g of x as the other dimension of the rectangle. Then the area a of x is equal to f of x times g of x and can be represented as the light blue region in the figure. Suppose f and g are changing by small amounts. The argument we will use works whether they are both changing positively, both negatively, or one positively and the other negatively. But for now, suppose that they both have a positive change. Our picture now looks like this on the screen. The change in area delta A is now comprised of three additional rectangles whose sum can be written as delta A equals f of x delta g plus g of x delta f plus delta f delta g. No matter how much the positive changes in f and g shrink, notice that f and g still stay the same. As the changes in f and g get smaller, just about all the change in area is taken up by the medium blue rectangles, and the dark blue rectangle area becomes negligible. So we can write now that delta A is approximately equal to f of x delta g plus g of x delta x. And that approximation gets better and better the closer the change in x gets to 0. So writing this in differential form, we get dA is equal to f of x dg plus g of x df. Dividing both sides by dx, we get dA dx equals f of x dg dx plus g of x df dx, which is, of course, our product rule. dA dx is equal to f of x times g prime of x plus g of x times f prime of x. Number 6 asks to use a geometric argument to show how the area of a circle changes. We know that if the radius r is a function of x, then a of x is equal to pi r of x squared and is represented by the light orange circular area. Now r is increasing, and the increase in the area of the circle is given by the darker ring. So dA is equal to 2 pi r of x dr, or if you want, dA dx equals 2 pi r of x dr dx. This is saying that the approximate change in area is given by the circumference of the original circle times the radius of its ring. So suppose that r equals 10 and delta r is equal to 0.1. Delta A, the true change in area, is pi, quantity 10.1 squared minus 10 squared, which is 2.01 pi. But we can approximate this change in area as 2 pi times 0.1, which gives 2.1 pi. In number 7, we show a geometric argument of how the volume of a cube changes. We can see what is happening in the exploded diagram. The blue figure represents our original cube. The yellow represents a cube that is grown. There are 3 rectangular solids shown by the red arrows that have been added to the original volume of the blue cube. There is also a tiny cube that has been added, shown with a blue arrow, whose volume will be negligible. And since we are approximating the change in area, we discard it. If the side S is a function of x, then the volume V of x equals S of x cubed. If S increases, then the increase in the volume of the cube is given by the area of the front times its depth, plus the area of its side times its base, plus the area of its top times its height, plus the change in side cubed, which will be negligible. So delta v equals s of x squared delta s plus s of x squared delta s plus s of x squared delta s plus delta s cubed. So dv is equal to 3 s of x squared dx, or dv dx equals 3 s of x squared ds dx.